Now we continue to learn Chapter 2, Determinants. Section 3, Additional Topics and Applications. Part 2, Cramer's Rule and Cross Product. Cramer's Rule. Let A be an n by n singular matrix and let B an n-dimensional real vector. Let AI be the matrix obtained by replacing the ith column of A by B. If X is a unique solution to AX equals B, then we know the ith entry of X, Xi, equals determinant of AI divided by determinant of A for all I varies from 1 to till n. So this theorem tells us that for non-singular matrix A, if we calculate the solution to AX equals B, each component of X can be represented as two determinants, and we do the division of two determinants. Okay, so see how to prove this. Since X equals A inverse times B, because A is non-singular, we know that because A inverse again equals adjoint of A divided by its determinant, then times B. And we consider these two terms, adjoint of A times B. So adjoint of A times B is just can be represented as B1 times A1I plus B2 times A2I plus T plus Bn times capital ANI. So this one is just the cofactor expansion along the ith column of AI. So Xi just equals determinant of AI divided by determinant of A. So this one convenient way to express the solution of the linear system by determinants. See an example. Use Cramer's rule to solve this 3 by 3 linear system. The solution. By Cramer's rule, we need to calculate the 4 determinants. Determinant of A, determinant of A1, determinant of A2, determinant of A3, where A1 is obtained from matrix A and substituting its first column by B, by the right-hand side vector B. So here is 5, 6, 9, and the other 2 columns keep unchanged from A. Okay, so determinant of A2 also, A2 is obtained by substituting the second column for A by 5, 6, 9 by the B. Similarly, we have determinant of A3. And using these determinants, we can get X1 just equals the determinant of A1 divided by determinant of A. So it's minus 4 divided by minus 4, so it's 1. And X2 equals minus 4 divided by minus 4 equals 1. And X3 here equals the determinant of A3. A3 is minus 8 divided by determinant of A. Determinant of A is minus 4. So we get is 2. So we get the solution of the linear system by using Cramer's rule. For Cramer's rule, we make such a conclusion. Cramer's rule is a convenient method for writing the solution to a linear system in terms of determinants. However, we must evaluate n plus 1 determinants of order n, which requires more computation than using Gaussian elimination method. So this rule is mainly for theoretical use. In practice, we still need Gaussian elimination. We still prefer to choose Gaussian elimination to get the solution of the linear system. And now we consider one product called cross product. The cross product, X cross product Y, is a vector. For X in R3, Y in R3, X product Y, cross product Y is also a 3-dimensional vector with each entry has a formula. For example, the first one is x2, y3 minus y2, x3. The second entry is y1, x3 minus x1, y3. And the third entry is x1, y2 minus y1, x2. It's not easy to remember in such a way, right? And if we constitute a matrix C in this form, okay, here, you see, C, the first row is W1, W2, W3 here. And we write the components of X in the second row, X1, X2, X3, and the component of Y in the third row of C is Y1, Y2, Y3. Okay, we construct this matrix, and this matrix is a cofactor, helps us to remember the components of X cross product Y. So you see, X cross product Y equals C11, the cofactor of 1 entry in C. So C11 times E1. E1 is a vector with components 1, 0, 0. And plus C12 times E2, cofactor times the second coordinate vector 0, 1, 0, E2. Okay, plus C13 cofactor, you get times E3, where E3 is a coordinate vector 0, 0, 1. And also you can get determinant of C just equals W1 times C11 plus W2 times C12 plus W3 times C13. So look at this expression. So the new vector obtained by this cross product X and Y will provide you a vector, say Z, new vector Z, such that Z is perpendicular to X and Z is also perpendicular to Y. Why we can see this? From this expression, if we substitute W1, W2, W3 by X1, X2, and X3, you will find its determinant equals 0, right? And this determinant equals 0 means W1 times the first component of this cross product plus X2 times this second component of product times plus X3 times this cofactor, the third component of this cross product. So this one equals 0. This means X transpose times this Z equals 0. So this vector is perpendicular to X. Similarly, if you replace W by Y1, Y2, Y3 here, you will still get determinant of C equals 0. So this means Z and Y, the two vectors, they are perpendicular, they are orthogonal.